In this video, we're going to go over what critical points are, why they're defined the way that they are, and how you can use them to find relative extremes. Let's dive in. So here's the official definition of a critical point. Basically what it says is that we have a critical point at any x value where the first derivative equals 0 or does not exist. And that does not exist part is actually important. You can't just ignore that. We'll talk about why it's important later. One other thing that's important to point out is that the original function has to exist at that point. That's something that students often forget, but if the original function does not exist there, it's not a critical point. And again, we'll talk about why exactly that is in a second. Basically, to make sense of this definition, it seems like really specific, but the way I think about it is that a critical point is a potential relative extreme. So in other words, it's a potential relative max or a potential relative min. And the key word there is potential. So a critical point is a point that might be a relative max or a relative min. It's not guaranteed. We actually need other techniques like the first or the second derivative test to verify that. But points where the slope is 0 or does not exist are the functions where we could have a relative extreme. So if you think of a method to find like relative mins and maxes, basically what we're doing here, the reason we care about critical points at all, is that if we can find a method that reliably gives us all the critical points, we can't guarantee that everything in that list is actually a relative min or max. But what we can guarantee is that all relative mins or maxes are in the list. So it basically gives us a finite amount of points to check using our other tests, like the first or the second derivative test, where we can actually confirm whether those points are relative mins or maxes. If we didn't have critical points, we would have to check an infinite number of points, which isn't possible. So these are important because they give us that smaller finite list that we can then apply our other test to verify whether they are relative mins or maxes or not. And that is the key point. It's basically you need critical points just to make sure you haven't missed any relative extremes. But again, you could have certain numbers in the list that are not relative extremes. So why are we looking for points where the derivatives are either equal to 0 or don't exist at all? It's because those are the only spots where a continuous function can turn around. Think about it. If I'm looking, and again, this is a really kind of ugly function I made up just to make a continuous function that shows all of the corner cases. But basically, if I go here, think about it. Where is the derivative equal to 0? It's equal to 0 at x equals 4. So this is a critical point, and we would be able to detect this by just taking the derivative of our function and setting it equal to 0 and then solving for x. However, here you can see that even though it's a critical point, it's actually not a relative max. So this is actually a situation where we have one of those critical points that turns out later not to be a relative min or max, or not to be a relative extreme. I've heard this called different things. One thing is like a terrace point, because if you look at like the side of a roof with a terrace on it, it would go up, level off, and it kind of has another roof. So that's just one word. But basically, yeah, even though the derivative is 0 here, even though we are leveling off, it's still not a relative extreme. But it's still a critical point. So that's why we would care about it. The next point, remember, a critical point is any point where the derivative equals 0 or does not exist. If the derivative doesn't exist, that would mean we're dealing with a sharp corner or cusp. So right here, actually, you can see that we instantly, as I transition across here, we instantly change the slope from a very high positive number to a very low positive number. So the derivative actually doesn't exist there. It's not even differentiable. But again, we still care about that because think about it. Even if the derivative doesn't exist, we could still have a sharp corner where we turn around. And that's exactly what's happening here. So even though the derivative does not exist here, it's not differentiable, it actually is still a relative max. That's why that part of the definition was so important. We can't just ignore where the first derivative does not exist. We actually need that because that's basically we need it so we don't miss points like this where we have sharp corners that actually just so happen to be a relative max or min. So that's good. Where would the next critical point be? Hopefully it makes sense that that would be at x equals 0. Why would that be? Basically because the slope is 0 there. And again, this is actually an example of a critical point where the derivative equals 0, and it actually is a relative min. So here, this actually is a relative min. This y value is less than all the y values right next to it. So this is a case where the derivative equals 0, and it actually is a relative extreme. And then let's look at the fourth case. Here you can see we also have a sharp corner here. So as I transition, you see how it instantly changes slope. It doesn't smoothly change slope like it did here. It instantly changes the slope. So there's a sharp corner there. So this is also not differentiable. So this would also be considered a critical point. However, it's not a relative extreme. So it's not a relative min or max because at this point, the value of the function, the y value, is not bigger or smaller than all the values right next to it. So there you go. Hopefully these four corner cases now make a lot more sense. That's why the definition of the critical point is the way it is. It's so that we can catch any points where we might be turning around, which basically happens whenever the derivative exists and the derivative is zero, or it could also be when the derivative just plain doesn't exist. But we don't have a guarantee with either of those. So I'm showing an example of one where, like, here's where the derivative equals zero, so it's a critical point, but it actually turns out not to be a relative extreme. Here's where the derivative does not exist, so it is a critical point and it turns out to be a relative extreme, a relative max. Here's where the derivative equals zero and it turns out to be a relative extreme, a relative min. And here's where the derivative does not exist, but it turns out to not be a relative extreme. So those are the four corner cases, and that's why the definition of the critical point is exactly the way it is. So there you go. Hopefully that makes sense. Hopefully it now makes sense why we care about critical points and how we can use them to find a list of potential relative extremes while guaranteeing that we don't miss any. If you have any questions, be sure to leave them in the comment section. Otherwise, I will catch you next time. See you.